almost 5 after. And I see the thing appearing live on YouTube. So I don't need to introduce you again. So Thierry, go ahead and take this away.
Okay, so welcome back to the second lecture. So let me put back on screen and if there is the least problem of either not seeing what I'm doing or a problem of resolution like yesterday, don't hesitate to shout. Hopefully the resolution problem should be solved. So I've slightly adapted the plan of the lecture to adapt to the flow. Again, we are not running a marathon. So today we will continue our trip to letting a liquid land, continue with other notion, fractionalization, topology, and of course I will show experiments, not just stay on the theory realm. And if time permits, I will discuss the effects of perturbations on what we discussed last time, namely what happens when you add a lattice, when you add disorder. And this will transition us nicely to the third lecture, where we will discuss the notion of transport, and probably I'll just say one word on the dimensional crossover. Okay, so just as a recap of what we did last time, let me just go here with the slides. And again, don't hesitate if you have questions that you did not ask yesterday to ask them now. I just recapping very fast what we did yesterday. So we want to study a typical Hamiltonian for bosons. So this term here is written in the field theory fashion. So nabla psi dagger, nabla psi. If you want to think of it, think about kinetic energy being p square over 2m, where p is the momentum. And remember that in quantum mechanics, the momentum operator is h bar over I times the gradient. So if you apply p to the wave function, it will be a gradient of the wave function. So this first term here is p square over 2m, the kinetic energy. Then I have the interaction term, which is usually taken as a contact interaction. Do you see the cursor correctly on the screen? Super, thanks. Which is usually taken as a delta function interaction in most of the cold atoms experiments, but I don't need it for doing the theoretical study. I could put any, let's say, interaction that I like here, and then of course a chemical potential. We will not discuss it directly, but I could also, of course, study the same version of the problem on the lattice. You heard Emmanuel talk many times of the Bose-Hubbard model, where there is the kinetic energy written in tight binding form, and then some contact interaction on sites and the chemical potential term. One can use exactly the same technology than we discussed. And this technology was to essentially rewrite the density using one collective variable, which I call phi, and you can think of this variable literally as a displacement of particles from a crystalline structure where the particles would be perfectly forming a regular crystal. So if phi is equal to 0 everywhere, this would be the perfect crystal. You see that the density would oscillate with oscillation at 2 pi rho 0, which is the natural distance between particles in a crystal. And the various harmonic are reconstructing delta functions by putting more and more harmonics. So you can view this as a kind of Fourier decomposition of the density. The long wavelength part of the density, it's the traditional hydrodynamic part. You compress and you expand the crystal at a long wavelength compared to its lattice spacing. But then there is simply the fact that you can shift the maxima, the position of the density, without distorting the crystal, but by just shifting all the particles by a constant. The constant would be phi here. And this, of course, shifts the place where the density has delta peaks. So this is something you should take into account. Then there is another collective variable, which is the phase of the wave function of the single particle operator. And these two variables are actually canonically conjugate. This is the traditional conjugation between coherence of the phase and number of particles that you know and love in superconductors and superfluids. So if you want, the gradient of phi is the momentum conjugate to theta, or by integration by part in this equation, the conjugate of phi is the gradient of theta, 1/pi times the gradient of theta. And then, as we discussed last time, by replacing simply in the Hamiltonian the expression of the density and in the interaction by their expression in terms of phi, and throwing away all the oscillating terms by saying, oh, they oscillate, so they will average to 0, they are not really important. We established that this very complicated bosonic Hamiltonian, which again, I want to emphasize, is a genuine quantum interacting problem. So you have, in principle, a 2 to the n matrix to diagonalize, if I could say, some exponentially large Hilbert space to diagonalize, but we could do it without effort, and the Hamiltonian reduces to a simple harmonic oscillator Hamiltonian, where essentially I can reduce all the effects to the knowledge of two parameters. One as the dimension of the velocity, and this is the sound velocity. It will describe how sound fluctuations of the density will propagate in the system. And the other is a dimensionless parameter, which I call K, which is of course dependent on the interaction, which is infinite if the interaction is 0, and which is something, if I am very naive, which would be 0 if the interaction is infinite. So here I represent it schematically on this term. But as we started to discuss last time, actually we should be a little bit careful of these expressions. And so just take these two parameters as parameters for the moment. And what we established, which is the most remarkable result, is the fact that there are correlation functions which are decreasing as power laws, which are dependent on some ultraviolet structure of the theory, so some cutoff, because we cannot sustain a linearized spectrum up to arbitrarily high energy. So if you want, I don't know very well the amplitudes here, but I know the decay, the power law decay as a function of distance between, for example, the creation of a boson at point 0 and the destruction of a boson at point R. And this decreases. This is the function G1, the single particle correlation function. This decreases as a power law with an exponent which is totally controlled by this exponent K. In the same way, the density correlations have various components. Okay, so that's just the average of the density. This is the long wavelength component, so the part which is not oscillating, and you see it's essentially decreasing as 1/x squared. Forget why, it's essentially two different times, so this would be the time essentially. This is the fluctuation of density of my bosonic system, which decrease as 1/x squared between 2 points separated by a distance x. But I have also the fact that the amplitude of the oscillation of the density, which is telling that I have a crystal. If I had a perfect crystal, the density would be 1 here, then go to 0, then be 1 after 1 period, then again be 1 after 1 period, then again be 1 after 1 period. But because my crystal is not really ordered, the amplitude of this correlation is also decreasing as a power law. And you see that this power law is controlled by the same parameter K, but with, of course, a different functional form than the single particle Green's function. Sometimes this is called the G2 correlation functions. And so I can define a kind of phase diagram, if I want to call it, of how the system looks like. Well, if K is larger than 1/2, this decreases more slowly than this. So I would say it looks more like a superfluid than it looks like a crystal. On the other hand, if K is super small, this doesn't decrease very fast. This decreases super fast. So I would say it looks more like a crystal than it would look like a superfluid. So this is a very peculiar state of matter that people call a Tomonaga-Oettinger liquid. And you see that this is something which has a tendency to be both a crystal and to be both a superfluid. And of course, everything that I'm saying is zero temperature here. I'm just talking about quantum fluctuations. We'll discuss finite temperature in 1 second. But the system doesn't really know on what side it should order: crystal, superfluid, superfluid, crystal. And as a result, it has these two power laws, which traduce this kind of instability that the system has, but cannot satisfy because it cannot break a translational symmetry. Okay, let me do a little pause at that time and ask if there are questions. No? Okay. Yep.
I have a question.
Sure.
So you're it looks like from the way that it's been written that like the superfluid or the quasi superfluid and the quasi charge density wave can like coexist, like both having power law. But it reminds me of like a you know, in a KT phase where, you know, the exponent has to be like less than 1/4 in order for it to be like relevant, or like in order for vortices to not be relevant. So is there going to be a similar story here, or?
Oh yes, oh yes, oh buddy, yes. There will be BKT transition all over the place in 1 dimension. And we'll come back to this, so don't hesitate to ask me the question again. We'll come back to this when we will discuss the effect of a lattice, which will be superimposed to this. For the moment, I'm discussing the gas in the continuum, which is the so-called Lieb-Lininger model. But you could ask, what happened if I put a small periodic lattice? The small periodic lattice will be super happy to see this kind of tendency and will certainly favor it very much compared to superfluidity. And the system will turn into a Mott insulator. And this Mott insulator transition, as we will discuss, will be a BKT transition. So yes, this is BKT physics in all its glory. For people who are not yet familiar maybe with Berezinski, Kostelis-Thouless transition, this is a transition that exists or has been invented first for 2-dimensional classical systems. Here we are in a 1-dimensional quantum system, but remember there is the time axis. So 1 spatial dimension, 1 time dimension. Quantum fluctuations, this is very much like 1 spatial dimension, 1 second spatial dimension, and thermal fluctuations. So this is a standard mapping from a d-dimensional quantum system to a d+1 classical system, and we'll come back to this point. Yes. Are there other questions? Okay, it doesn't seem to be the case, so let's continue. Let me just mention something in the correlations. Let me just show, for example, again, this density correlation, delta rho of x and t, delta rho of 0 and 0. And so a delta rho is rho minus rho 0, just to suppress the average term. And then we had this term, which was sort of x square. So this is something which is sort of x minus vt square. Okay, it's not exactly correct what I'm writing, but it doesn't matter. And then there is the other term, which is cosine 2 pi rho 0 x times 1 over r to power, let's say, 2k. And R is a mixture of space and time that I don't want to discuss. Now let's imagine I'm doing a Fourier transform of this thing. So I'm now trying to compute this correlation G, but not in real space and time, but in frequency and momentum. What will I see? I will see that because, so let me trace this as a frequency and momentum. And now I would have a third axis, which I will not draw here, which is the intensity of the function. Well, clearly, I will have singularities that will occur at small momentum. And these singularities will occur when omega is u times k. So I can expect to have a lot of signal here when I am here where omega is u times k, and some line shape here, which I don't want to discuss. at that stage, which will result from the Fourier transform of this type of correlations. But you see that I have also power laws, which means very slow decay, which means Fourier transform will be singular when I am doing a Fourier transform around 2 pi rho 0. So it means that I can expect here around 2 pi rho 0 to have also singularities. And actually, it's not totally obvious to see, but I will have a continuum here of singularities. So I will have spectrum which will take place here in a kind of light cone around the point 2 pi rho 0. How I connect this thing is not important at the moment. So let me just do something like this. It doesn't matter. So I can expect to have signal somewhere like this. So this is something we can work out very precisely. Mathematically, it's easy to do the Fourier transform of this function, but I want to give you a flavor of what is the Fourier transform that this field theory is predicting. And you see that it's predicting a line here where which will be centered around omega equal u times k. And remember, u is a function of the interaction, the density of the particle, and so on and so forth. And then there will be some signal here, which is coming from this oscillation at 2 pi rho 0. And just to show you, because you could say, oh, this, does it work? Does it not work? Let me show you in the spirit also of combining several methods, what happens if I compare this with a very recent result. When I say very recent, it's still 14 years old, but believe me, by the time of Bethe-Ansatz, this is recent, where people computed from Bethe-Ansatz, from the exact solution of the Lieb-Lininger model, exactly the correlation that I discussed. Gamma is the strength of the interaction. So when gamma is small in proper kinetic energy units. So when gamma is small, the system is very weakly interacting. When gamma is large, the system is very strongly interacting. And if gamma was infinite, the repulsion between the bosons would be hardcore. You could not put two bosons in the same place. And this is something, by the way, which bears a name, which I think I should write somewhere. So when gamma is equal infinity, this is called the Tonks limit, where you really have hardcore bosons. We'll see that this is a very simple problem, the hardcore boson. Well, not so simple. Now, this is the exact solution. So again, same axis. Forget this kf. This is written k. When this is 2, this corresponds to 2 pi rho 0 in my units. So forget the correspondence and the denomination kf. For those of you who know the Tonks limit, you know what this kf means, but I don't want to discuss it for the moment. So this is the momentum. This is the frequency axis, again, in some units. And this is the intensity of the correlation function. And you see that this is roughly the k-square spectrum. But what you don't see here, because it's very, very tiny regime, is the fact that there is actually a linear part here. So we get this omega equal uk spectrum, but very rapidly it crosses over to a k-square spectrum, which is beyond the field theory, which I cannot describe by my field theory technique, but which is there, of course, in the exact solution. After all, if gamma was 0, I should have a k-square spectrum. These are the free bosons, so I should get the k-square. And you see what happens when you increase gamma. And you could say, oh, I don't see anything at 2 pi rho 0, so you lied to us. There is nothing. Well, you don't see anything because the total spectral weight here is so small that at the scale of this graph, you don't see any contribution. But believe me, there is something here. It's just very tiny. And then you increase gamma and you see several things. You see first that the linear part become more visible. You see also that the slope is changing, which is the sign that u depends on the interaction, which is not a surprise. I remind you that u was going as square root of the interaction, as we established it perturbatively yesterday. But you also see that spectral weight starts to appear here, And when you go to gamma equal 20, which is, let's say, large enough, you see indeed that there is significant continuum of excitation, which is developing around this point, 2 pi rho 0, in perfect agreement with the field theory prediction. So there is really good connection between what the exact solution of the Lib linear model can give you and what the field theory can give you. You see that the field theory is kind of giving you the bottom part of the spectrum here. This will be its strength. The exact solution can give you everything, but the field theory can be used even if the interaction is not a contact interaction, and tells you that the physics is essentially the same, which the better ansatz could not give you, because then you lose completely the solution. Okay, so, but it shows you that all these things are perfectly consistent between the various methods. One final element that I want to give, even if I will not go too much into details, but it's good to keep in mind, is of course we can do the same calculations at finite temperature. We have an harmonic oscillator problem, so it's totally easy to solve it at finite temperature as well. And then let me write for you the correlations at finite temperature. So if I was doing the thing,
can I ask something?
Yes,
about
of course.
I guess I forgot what sets this rho 0, and it's not changing with gamma, it seems.
Okay, so rho 0 is the average density of particles. So this is the number of particles per unit length, if you want. So this is something that I can perfectly fix once and for all. I can say I have 1 boson every centimeter. And I can keep it fixed and just change the strength of the interaction, which is what has been done here in these 4 graphs. I could also decide to change the average density of particles, and this corresponds to 2 different problems. For example, when you use a Feshbach resonance, you could say in first approximation, you maintain the density rho 0 constant, but you can tune the interaction as much as you want. You could also load the tubes with different number of particles, in which case you would change the density between various experiments. So again, in our expressions, rho 0 is just a parameter, which is appearing, for example, in this in the Hamiltonian, which is appearing also in the expression of the energy of the density, and therefore I can fix it once and for all. Say I know the density of particle, the average density of particles, and I can decide to work with 1 boson every micron, or 2 boson every micron, or something like this. Does it?
Right. Yeah. I was just, I guess, confused that I was thinking maybe if you increase the interactions, you change that density wave-like order to different distance or something like that. Maybe it depends on density. I was thinking something like that.
So again, the effective effect of the interaction will, of course, depend also on the density. So if you keep the interaction fixed, but you change the density of particles, you're de facto changing the effect of the interaction, because you change the ratio between kinetic energy and the interaction term. If you dilute very much the particles, they don't see each other very much. So you could say they are not really interacting very strongly. You have to be careful with this argument, because you're also diminishing their kinetic energy. So one has to be careful. But if I take, for example, the Fermi-Hubbard model, this is a faithful statement, and the particles simply don't see each other and don't interact when they are extremely diluted, or interact very weakly when they are very diluted. So these are 2 parameters that you can control totally independently: the strength of the interaction and the average density of the particles.
Thank you.
Sorry, can I ask a question?
Sure.
You know, the two regions that you've shown on this plot actually, I guess, correspond to having collective excitations, I guess, right? Due to
Yes.
the fact that, yeah. So what is the difference between the nature of the 2 excitations? Maybe you already said it, but I missed it.
Okay, so this is something which is very interesting if you think about it in terms of higher dimensions. When you think about a superfluid, then you think about the Bogoliubov approximation. What people draw usually, what you will find in textbooks, are graphs like this. They will tell you this is the Bogoliubov spectrum. This is the spectrum of long wavelength excitations, the sound waves. And this is what people call the roton, which is the excitations where you start doing kind of more complicated distortions of the density. What is very specific to one dimension is that this roton minimum here kind of goes down and touches the zero of energy, which describes actually the will of your system to form a charge density wave, to form a crystal. And this is a continuum. These two regions are smoothly connected. And by the way, this is not a line. This is a region which has a finite width, but the widths become thinner and thinner as you go to lower and lower energy. So this is what you would call a well-defined excitation, and that's the sound excitation that is propagating in our system. But this region here is mostly describing the fluctuations that corresponds to near crystalline order in our system. By the way, it's not just at 2 pi rho 0 that you get such thing like this. You get also something at 4 pi rho 0, 6 pi rho 0, 8 pi rho 0, and so on, because you see that in the density expression, you get all the values of P here. But every time you're increasing also the coefficient of phi, so you're changing the exponent. So the exponent that is 2k is only valid for 2 pi rho 0. If I was going to 4 pi rho 0, I would get an exponent which is 8k, and so on. So this is decreasing faster and faster. So this has less and less spectral weight. But this is one of the remarkable prediction of this Tomonaga-Luttinger liquid, which is that there are also minima at other momenta, potentially. And these minima are controlled by the same parameter k than the one which exists at 2 pi rho 0. Now, for some specific models, like the Lieb-Lininger model or others, some of these minima could be absent because these unknown amplitudes that I have not tried to compute here, A1, A3, could be 0. So you could lose some of this resonance if you want, but a priori for a generic model, you will get cosine 2 pi rho 0, cosine 4 pi rho 0, cosine 6 pi rho 0, which will be present in the density correlation. And this is the tendency to form a crystal, but a crystal which has strong quantum fluctuations, which tend to disorder it. And that's why you lose the perfect positional order of the crystal. Does this answer your question?
Yeah, it does. Thank you.
Okay. Unless there is another question, let me go to finite temperature. So let me just give you the formula, which was the average of exponential of 2 phi of x exponential of minus I 2 phi of 0, which is essentially the delta rho correlations that I've written. Actually, when you work out this correlation, you find that this is exponential of minus 2k log of x, and that's how you get this power law. If you go to finite temperature, what you will find is something which is exponential of minus 2k, and I'm slightly cheating you, but it's not very important at that stage, beta times hyperbolic sine of x over beta. And again, this is an harmonic oscillator problem. So you can just solve the problem at finite temperature, you know, and put all the Bose factor for your harmonic oscillator and blah, blah, blah. And this is what you will get. And so you see what happens. If x is much smaller than beta, you expand the hyperbolic sign and you recover exactly the same formula. So the correlation function is essentially decreasing as a power law as before, 1 over x to power 2k. But then you pass essentially a certain distance, which is of the order of beta. And then you cannot expand the hyperbolic sign anymore. And the hyperbolic sign is essentially exponential of x over beta. And the log of this is essentially x over beta. So you find that this is now decreasing as exponential of minus whatever, 2k over beta times x. So you find now that the correlations are decreasing exponentially with distance. And that's normal because at finite temperature, your quantum problem becomes a classical problem. And you know at long enough distance that in 1D classical problems, all correlations should decrease exponentially. So you have this very interesting crossover between the power law that you expect for a quantum problem at 0 temperature at short distance, followed by the very natural exponential decay that you expect for a 1D classical problem. There is a very nice conformal way of dealing with this result, which I won't discuss, but this is one case where conformal field theory can help you also with these things, because having finite temperature is like having the imaginary time on a finite circle instead of being infinite, and therefore you do a mapping of the plane, the 2D plane, onto a cylinder, and you can recompute these things by conformal transformation for people who are specialists. But forget about this. The only thing we need to know is that at large enough distance, if we are at finite temperature, we should recover something that will be essentially the exponential and exponential decay of the correlation functions. So just to explain what was on this slide, which is that you will get this exponential decay. By the way, as a little numerical trick, if you do Monte Carlo or if you do calculation at finite temperature, you see that the length, which is giving you the exponential decay of the correlation function, is not beta. It's beta multiplied by or divided by k and 2 pi and blah, blah, blah. So actually, if you can measure numerically this length, you get a very efficient way to extract the parameter k. So this is a very nice technique to extract from a numerical study of the problem at finite temperature, this parameter k, which is relevant for the quantum problem at 0 temperature. You extract it from a fit of the exponential decay of the correlation function. And we will come back to this discussion a little bit later. Okay, I won't insist on this because I will focus on bosons essentially in these 3 lectures, except otherwise specified. But just as a teaser, you can use this bosonization technique not only to describe bosons, but to describe spins and to describe fermions. So I'll just flash the spins because we won't use them very much. Actually, spin 1/2 is a boson, is a hardcore boson, because if you have a spin down, you could say I have no boson on the site. If you have a spin up, you could say I have 1 boson on the site. But you cannot have anything else. So you need to limit the Hilbert space to 2 states. And therefore, you put the hardcore constraints that you cannot have more than 1 boson per site. And spin operators on different site commutes. And it's very easy to check that S plus is B dagger, S minus is B, and SZ is B dagger B. It's the number of bosons per site minus 1/2. So there is an exact mapping between spin 1/2 and hardcore bosons. This mapping is true in any dimension, and it's a very useful mapping, a little bit unpleasant because the hardcore constraint is not very easy to implement in terms of practicality. So you can use the bosonization formula, because I told you I don't care what is the interaction, hardcore, no hardcore, whatever. You can map spins. So here are the bosonization formula for spins. And these bosonization formulas have a very nice interpretation. The variable phi and theta, so again, you find correlation functions which are power law, but you can view the phi and theta as the polar and the azimuthal angle of the spin 1/2. Phi is the angle from the vertical. You see that SZ is cosine 2 phi. So the larger phi, the more XY is the spin. And theta is the projection, is the angle which characterizes the projection of the spin in the XY plane. Okay, I just mentioned this, but since I won't use spin, I won't spend time discussing too much the formulas for spins. I just want to mention that you can do fermions with the same trick. And now you could say, how can I do fermions? Well, you do fermions the same way that you do bosons, exactly the same formula for the density, except operators of fermions need to anti-commute, not to commute. And I know how to express the operator that commute in terms of phi and theta. We already did it for the bosons. So I just need to multiply this by a phase, and this phase is exactly exponential of 1/2 of phi L of x. And this phase will ensure that it's transforming the commutator into an anti-commutator. So I leave it to you as an exercise. If phi b is commuting, and if I have the canonical commutation relation that I introduced before in terms of the phi and theta, you can check that this new operator, which I call psi dagger f, is now anti-commuting and has the anti-commutation, the canonical anti-commutation relation. So this is a fermion operator. So if I know how to express this phi b in terms of phi and theta, I know how to create a fermion operator that satisfies all the nice anti-commutation rules that I would expect. Again, we will not use today fermions, so I don't want to insist. I just want to make one remark, because I have added here an extra phi L, which is an extra phi. Now, the sum of a p, which for bosons only contain 2p here, so there could be 0. And then this term was completely away, and I had one term which only contained exponential of I theta. Now it's impossible, because if I choose p equals 0, I will get one term like this, which is essentially this one. And if I choose -1, I will get the same term with the opposite term. So fermion operators cannot contain just phi or theta, but they need to contain both operators. And this has two consequences. The first one is that you see that the fermion operator has no classical limit. You cannot say, I order the field theta, and this object is ordered, which was the case for bosons, because now phi would be maximally disordered. So this is reassuring. And the second one, you see that if I choose p equals 0, I have objects that oscillates with pi rho 0x, which corresponds to kf, the Fermi wave vector. And if I choose p equal -1, I have an oscillating term at -kf, and I recover what I should recover, namely, if I want to deal with fermions, my low energy properties, whatever is my dispersion relation in energy as a function of k, it doesn't matter what it is, but my low energy properties will be dominated by excitations which are around the Fermi points. And so I have two types of particles. The particles which have a momentum which is close to plus kf, which sometimes people call the right movers, and particles which have momenta which are close to minus kf, which are the left movers. And you see that this bosonization formula that I showed you naturally introduce these two species of particle. So there is actually a much more historical version of bosonization, which was directly done on the fermions, where people start from this, linearize completely the spectrum. It's not something I want to do, but linearize completely the spectrum. So create essentially a Dirac equation, if you want. And then you apply a certain number of mathematical transformation, and you arrive exactly at the same formulas than the one I've shown. The advantage of the procedure that was introduced by Haldane is that first, it's very physically transparent, and B, it shows you that it doesn't matter what is the statistics of the particle, fermions, spins, bosons. The only important things is that you express the things in terms of these collective excitations that we discussed before. But I just want to emphasize, even if today we will concentrate on bosons, I want to emphasize that this method is totally generic, and you can use it for fermions, you can use it for spins, you can use it for bosons. Okay, so I think we are more or less done in terms of the technique, and I reassure you, we did. So again, here are density correlation for fermions that you can write, and again, this is power laws dependent on this parameter k and so on and so forth, but I don't want to go too much into details. Okay, so the last nail in the coffin, if I could say, is, or if you want, the last stone in the superb cathedral is to say, after all, when I was doing this, I was throwing away a lot of terms. You know, how much of this is reliable? And there, I would say, in the 70s, people perceive this type of formulas as kind of approximate formulas, but in a way that was difficult to control. It was kind of difficult to know what was good and what was not good, and so on and so forth. And the things became clear. Tomonaga, Lettinger, liquids became clear with a very famous paper by Duncan Haldane. It's not the one for which he got the Nobel Prize, but it's another one for which he could have gotten the Nobel Prize, because it's a wonderful paper, in which he sort of says and realizes that this Hamiltonian is actually, as I was saying, you should think of it as a fixed point Hamiltonian. Namely, this is the Hamiltonian that contains the most relevant operators that will control the asymptotic physics of most 1D systems. And we'll see exceptions, don't worry. The physics of 1D system is not just harmonic oscillators, but most systems in the continuous and the continuum and whatever. And as any fixed point, one should be very careful of the details, and essentially the form of H and the operators is exact. Namely, all my structure of density with all these harmonics and whatever, this is perfectly exact. So for example, the exact relation that I have between the exponents, this I have no reason to change. For example, when I say I have here an exponent which is 1/2k for the single particle correlation, but I have an exponent which is 2k for the density correlation, this is the inverse of the other. This is an exact relation. I don't know what is k, but I know that this relation is exact. And this is something that can be tested, by the way. But what is not exact are the perturbative calculations. So U and K must be determined from the microscopic model. You could add other things like the amplitudes as well. As I said, I was not very careful to tell you what these A1, A3 are, but technically I don't know them, so but they can be determined. So it means that, for example, this formula that I wrote, which is that K is 1/√G, this is wrong. It's a perturbative formula. It will be corrected by all the irrelevant operators, the oscillating terms and whatever that I have thrown away. But if I have a trick to compute this U and K exactly, then I get essentially the exact asymptotic properties of the system. So this is a remarkable result because it opened the road to a fantastic program that people have implemented in the last 20 years very efficiently. I mean, even if it started, the paper of Haldane is from 82. So this has started a long time ago, but recently we could really nail it down, which is the following. If you need short range, short time, well, use numerics or Bethe-Ansatz or whatever. Then when you will go to long range, long time, the numerics is dead. And for most model, Bethe-Ansatz is dead also. And you have a field theory which depends on two parameters. So use the exact solution. And the exact solutions could be, and we'll see what it means, could be Bethe-Ansatz, could be numerics, etc. Sometime intelligence does it, to compute the exact values of U and K. And as I said, if you can, the amplitudes. But this is more difficult. And then you have essentially an exact field theory. And so you can sort of combine the best of both worlds by saying, if you want, in the omega, let's say, energy scale, I could say I use numerics till here. And then my field theory would be valid till here. So field theory, numerics. And if I can inject from the numerics the exact parameter U and K, I have essentially an exact description which is valid at all scales of my problem. That's a remarkable scenario which allowed essentially to get, to clean up 1D systems. Again, in simple situations, because again, as I said, one urban legend is that everything is understood in 1D, which is definitely not true. Now, how can you determine easily the U and K? And why is it better to determine U and K than say, I use the numerics to compute the correlation functions? Imagine you have a system of 20 sites because you do exact diagonalization. It's very hard to compute the correlation functions. You have not many sites before you hit finite size effects and so on and so forth. But U and K control everything. So for example, you can compute the compressibility of the system. It's a thermodynamic quantity. It suffers from very little finite size effect. It can be computed even with simple techniques like exact diagonalizations. And if you know the compressibility, you know it's a certain function of U and K. So you just need a second equation like this, and you can extract out of two thermodynamic measurements the parameters U and K. What are the good methods? Depend on your numerical technique. Bethe-Ansatz people like to compute compressibility, and then they very often get the spectrum of excitation, so they can give you U directly, or they can compute the response to a twist in boundary condition of the system. So they give you the product U times K exactly. Compressibility is essentially U over K. Response to a twist in boundary condition is essentially U times K. DMRG people use the compressibility, U over K. And then because they are in a box, it's not so easy. But they have big systems. So they compute the correlation function, the static correlation function. They fit the decay and they give you K. And that's it. Then you can compute dynamical correlation function, finite temperature correlation function, more complicated correlation functions out of the field theory. So this is a very nice program, and I'll try to show you a couple of examples of how this was implemented. And that sort of made the concept of Tomonaga-Oettinger liquid extremely useful, because as I said, now it's a powerful weapon to really extract physics with a very strong predictive value from either a microscopic model, or even if you have an experiment, you do 2 experiments to measure these 2 parameters U and K, and then you inject them in a 3rd experiment to see that it is consistent. So this is something that can be done very efficiently. So here is the paper. I was wrong. It's 80, not 82. And this is the paper in which Duncan Haldane realized that there are very exact relations. And he provided at the time from the Bethe-Ansatz for the Heisenberg chain way to compute this parameter U and K, which he had different notations. So Vs and Vn are combinations of the U and K, and this is something you can do. So I strongly encourage you to read this paper. It's not particularly easy to read, but it's a very, very, very beautiful paper. Here is the thing recast in the language of K, for example, for a spin chain. This is as a function of the ratio Jz over Jxy. And this is as a function of the magnetization of the chain. So we know exactly these curves and the limiting values of the parameters. The values themselves have very little influence. You can do the same thing for the attractive Hubbard model, the repulsive Hubbard model, and now any model that tickles your fancy, one can extract this type of parameters. So you can do a quantitative analysis. As I said, this is just re-saying what I mentioned. I give you a little set of measurements that you can do. Specific heat is the temperature divided by U. So if you can measure or compute the specific heat, you get the parameter U. Finite size dependence of the energy of the ground state is giving you the parameter U, and so on and so forth. You can extract a certain number of things from even more complicated measurements. Let me give you one example where there is no need to do any calculation, which is this famous Tonks limit, because I think it's a beautiful example which illustrates very well the methods. So let me just illustrate this on the Tonks limit. So the Tonks limit is hardcore bosons. So people realized very rapidly one thing. I'm sure you heard about the Tonks limit already in one of the previous course, although now I listened to them, but I don't remember if someone mentioned Tonks limit. There was some mention of it? No? Okay. So let's say you have hardcore bosons. Now, let me plot the wave function psi as a function of x. This is the wave function for one coordinate, so the coordinate of the first boson, for example. And this is the position of all the others, x3, x4, x5. I put them semi-regularly, but there is no reason that they are. Now, if I am in the hardcore limit, by construction, it costs me an energy which is infinite to put 2 bosons on the same site. So it means that whatever the wave function is doing, it has to go to 0 when 2 bosons would be on the same point. And because the wave function is symmetrical, then the wave function should kind of recover and do something like this in between the bosons. But this wave function has nodes every time one boson crosses another boson. And so what people realized is that if you do a transformation, which is a little bit complicated on the wave function, by just changing the sign of the wave function every time you cross, what you get here is what? What is this wave function?
A slighter determinant.
Yeah, it's a wave function of 3 fermions. It's a wave function which now changes sign every time 2 particles crosses each other. So the Tonks limit can be mapped onto a free fermion problem. So this is a problem which is particularly simple to map. Wait. Because actually you have the wave function of the bosons and you have the wave function of the free fermions. But these two wave functions are not identical. One is a complicated transform of the other. So actually, the problem can be mapped onto a free fermion problem, so it's simple to solve. But if I want to compute observable, I still have to undo this transformation. So there are cases which are super simple, is when I have the modulus square of the wave function, because then the sign doesn't play any role. So anything which is densities, currents, blah, 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 they are the same for fermions and bosons. But if I want to compute, for example, the single particle Green's function, this one is not the single particle Green's function of the fermions. So I emphasize this is not the free fermions. And you can compute it because the transformation can be mapped, and this has been done. There are nice paper by Dima Gangart in particular, which is doing this. But if I have my field theory, I don't need to do this. I will just use the fact that I need to determine K, let's say. And if I know K, I know that this correlation function is decreasing as 1 over x to power 1 over 2k. We established it. So if I know the K, and that I can extract from my knowledge that this problem is free fermions, I know how the single particle bosonic function decreases. How do I do it? If I have free fermions, I know that delta rho fermions of x, delta rho fermion of 0, it's something that has an oscillation at 2kf. It's called Friedel oscillations, and it decreases as 1 over x squared. But I know that this should be 1 over x to power 2k. So it immediately tells me that k for g equal infinity is equal to 1. So without any calculation, I can tell you that if I set the contact repulsion between bosons to infinity, the Luttinger parameter has to be 1. Otherwise, I don't have the proper density-density correlations. And now I can tell you that the correlation function of the superfluid, if you want, is decreasing as 1 over square root of x. So it's still pretty slow decay, even if I have a contact repulsion between the bosons. It's still a pretty slow decay. And this is something you can compute without undue strain by using this little trick. Of course, for intermediate value of the repulsion, you have to use a more sophisticated technique, like, for example, using the exact Bethe-Ansatz solution of the Lieb-Lininger model. But for really the Tonks limit, it's not complicated to obtain this limiting value. Okay, can one test all these nice things? And so let me just show you a couple of tests. I won't discuss very much the condensed matter side. We'll switch very rapidly to cold atoms, just to show you that, of course, people had already started to test these concepts in condensed matter. I show you this condensed matter object here, which is an organic superconductor, which is made by stacking molecules like plates, if you want, because they reproduce a little bit this concept of tubes, which are very weakly connected that we already discussed and which is very natural in the cold atom context. So this tells you that this type of materials will have these dimensional crossovers that we were discussing. But just to flash one result, in these materials, you can measure, for example, the frequency-dependent conductivity. And if you do the calculation based on Luttinger liquid theory, you find that it should be a Paolo, not surprising. And lo and behold, actually, people did the measurement and they find a very nice Paolo. And to the best of my knowledge, this was the first time that people could test Tomonaga-Luttinger liquid theory on a metallic system, on an itinerant system. Okay, let's not discuss too much the condensed matter. Let's go to cold atomic gases. And indeed, cold atomic gases have provided a cornucopia of low-dimensional systems. So let's start with one of the earliest experiments that was done to observe indeed whether one could get this transmutation of bosons into fermions, if you want. Again, I beware of this. It doesn't mean that bosons start to have anti-commutation relation. Bosons are bosons. They still continue to commute and have symmetric wave functions. But to see that there would be this kind of mapping onto a free fermion gas. And this was a beautiful experiment done in the group of Dave Weiss, where he realized several tubes by the technique that you know and love of optical lattices. And then by squeezing the tubes, he managed to increase the repulsion, because the difficulty is to get the system with strong enough repulsion. And lo and behold, when he managed by tricks that I don't want to discuss to compute the energy of the system, you see that the curve that he obtained was not fitting at all the free boson or nearly free boson curve, but was more tending, this is the experimental curve, the dots here, but was more tended, this is the free fermion limit, but was more tending towards the free fermion limit. And the line is essentially what you would get by the Bethe-Ansatz solution of the problem. So this was a very nice indication that indeed one could realize these 1D gases and tune their interaction large enough. Note the repulsion here, which is pretty large. This is the same parameter gamma than you saw in the previous slide. So you see it's not getting to 20, but it's getting to 5, and you get already pretty good proximity to the Tonks limit. Another beautiful experiment on this was done by Emmanuel Bloch. I'm sure you recognize him, even if the experiment was 2004. Same thing, obtaining tubes, which are 1D tubes. And then he could not modify the repulsion because at the time they had no Feshbach resonance. So he used another trick, which is to simply kill the kinetic energy by putting an optical lattice along the tubes, which was making very hard for the boson to jump. And with that, the ratio of interaction towards kinetic energy was going up, 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 and then he could reach the Tonks limit. Does someone see a potential inconvenience of this method compared to using a Feshbach resonance?
Is one biasing towards the charge density wave?
No, because again, you're biasing towards the charge density wave by increasing the interaction. But as we discussed, you would have needed to reach k equal 1/2 to really go to the charge density wave. You're right, the lattice could have locked the charge density wave, but the filling is sufficiently incommensurate with the periodicity of the lattice that it's not a major problem.
Is it slow?
It's probably slower. We should ask Emmanuel whether this was a factor which played a role. But the first inconvenience is the temperature. Because actually you lower all the energies of the system, but the temperature is what it is. So actually you get warmer bosons relative to other situations. So you have to make sure that you're not polluted too much by thermal effects. Otherwise, you will not look really at the problem close enough to t equals 0. He measured the momentum distribution by time of flight. And here is what they see. This is the momentum distribution, for various situations as a function of the momentum. So k is the horizontal axis, n of k is the vertical axis. And essentially, straight lines are kind of power laws. Now, is it a beautiful 1/square root power law as we would expect? Why?
Because of the confinement?
Yeah, the problem is that this experiment is not done in a situation where each tube has the same density, but is done in a situation where essentially the density is going from maximum in the central tube to practically zero in the peripheral tubes. So this is a mess. And this mess caused by the confinement will become worse in 1D because everything depends on the density. The velocity due depends on the density. The exponent k depends on the density, and so on and so forth. So you saw me making a face when there was mention of the trap the other day. I have 3 wishes for cold atoms. The first is get rid of the trap. The second is get rid of the trap. And the third is get rid of the trap. And this is a wish which is fortunately shared by many experimental groups, but of course it's super complicated. So keep in mind that these are very early experiments, and this is 2004. And that's why now that you get these beautiful boxes which have been realized, and also a microscope which allows you to measure locally things, and that makes it much more easy to really identify behaviors like the one that we are discussing. Nevertheless, here, because the system is simple enough, it's 3 fermions, you can, of course, solve the problem in the confinement. And you see that there is very beautiful agreement between the theory, which is the lines here, which is not a simple power law anymore, which is a power law complicated by all the confinement, but which you can solve by using LDA, and the observable, the observed situation. Another experiment where people tried to and succeeded in observing power law of Tomonaga-Luttinger liquid is provided by Atom Chips. This is the group of Jörg Schmidt-Meyer. And here, this is done by doing interferences between 2 tubes. And the theory was done by the late Adilet Imambekov, Gritsev, and Eugene Demler. And what is measured in doing an interference between these 2 tubes is essentially the correlations between the function in 2 different points of the tube. And you can measure this interference by choosing a window of size L. So what is measured is this correlation function. And this correlation function, because the tubes are at relatively high temperature, behave as a power law. Behave as an exponential of minus x over L. But you can check that this is consistent with what is observed experimentally. And again, lo and behold, people did matching about the amplitude which is measured in the interference figure as a function of the size of the interference window. And this is in good agreement with these predictions that we are discussing. This experiment is very, very far from the Tonks limit. The Luttinger parameter in this experiment is about 40. So this is a very weakly interacting Bose gas, contrarily to the 2 previous experiments that I showed you that corresponds to relatively strongly interacting Bose gas. Okay, you can do the same thing for fermions. I will not go too much into details, but you can measure the velocity U that we were discussing. This was done in the group of Randy Hewlett, and we helped a little bit with the theory. Piotr Grisin did the theoretical analysis. So this is fermionic systems, and the measurement which is used is the so-called Bragg spectroscopy. So Bragg spectroscopy is actually a technique which allows you to measure, sorry, I have to reactivate the iPad, if it can nicely allow me to log in by looking at my face. Voila. Bragg spectroscopy. Why did it stop broadcasting? Oh, let's do it that way. Should come back in 1 second. Tuck. Voila. Poof. Et voilà. So Bragg spectroscopy is a technique that will measure the density-density correlation function at a fixed momentum by scanning the energy. So it's like doing a scan here of this correlation. So what you expect to see is a peak And this peak will be located at a position in energy that will be u times the wave vector that you know and that you control by putting your laser at a given position. So in this experiment, what was done was to measure for various values of the interaction between the fermions, the position of the peak that was observed in the system. And lo and behold, by doing the proper analysis of the position of the peak, you could compare with a theoretical prediction of what this velocity should be as a function of the strength of the interaction from the model of two-component fermions in the continuum, which is called the Gaudin-Young model, which is another integrable model. And this was fitting pretty well between the experiment and the theory, which made some people say that ultra-cold atom confirmed 50-year-old physics theory, which was the Gaudin-Young model prediction for the velocity. I don't know if it should be considered as a compliment or an insult, but I think this was a pretty cool experiment and pretty nice matching between theory and experiment. Okay. So let me, in the couple of minutes that I have to finish, mention other important, very important properties of 1D excitations, because I showed you that you get these excitations that are leading to power law correlations and so on. But it's not the only thing that is very characteristics of 1D. And one thing which is extremely important is that you can get a phenomenon which is known as fractionalization of the excitations. And let me try to illustrate on a little cartoon what I mean. Let me take the Heisenberg model, the spin Heisenberg model, because it's the simplest. We'll move to other systems. So imagine that I have an Heisenberg model like this, and let me draw not the ground state, it's not the real ground state, but the cartoonish ground state, which would be an antiferromagnetic up, down, up, down, up, down situation. If you try to create an excitation in these systems, well, what you can do is to flip one of the spin. If you do this, the minimum quantum number of your excitation is delta S equal -1, because you went from a spin +1/2 to a spin -1/2. So that's the best you can do. And this excitation in high dimension, as a name, it's called a magnon. And this is like a particle. This is an object. Here I created it locally, but if instead of creating it locally, I would create it with a given momentum, it has a good dispersion, E, as a function of its momentum. And so people have measured these magnons in magnets by using neutron scattering experiments and so on and so forth. But whatever is this excitation, the minimum excitation that you expect to do is delta S equal -1. There is no way you can do less than that. Well, it's not true in 1D. It's not true in 1D, and let me illustrate it for you. Let me now redo my magnon, but now I will apply the Heisenberg Hamiltonian to do dynamics of this magnon. So there is here S plus S minus term in the Hamiltonian. So the S plus S minus sort of invert two spins, flips two spin. It lowers one spin and raises the neighbor. So let's do it. Let's apply it several times. So I do this on these two spins. I do this again. And then I do it a little bit faster on the rest of the chain. And now look at what happened. My magnon, which is essentially 3 spin down close together, has disappeared. It doesn't exist anymore. What I get is a weird situation where I get 2 spin down, which are close to each other, and then followed by a chain of spins, which are in reverse position, their original position. And then again, 2 spin down close to each other, and I get back to the original spin position. It's like if my magnon has split into 2 excitations, and trust me on this, this excitation carry a spin 1/2 as they should, because this excitation plus this excitation should reproduce the total quantum number that I had before. But this excitation is actually not local, even if the little circle here make you think that the excitation is local. It's not true. It's there, but it's followed by a string of completely turned material. So what happens in 1D is that an excitation which is local can fractionalize by splitting into two non-local excitations, which could not exist individually, because to create it, I would need to do a non-local transformation on the system. But this excitation, quite remarkably, can carry a quantum number which is smaller than the minimum quantum number you would expect for a possible excitation. It's like if you could take an electron and cut it into two subparts, each one carrying a charge 1/2. I don't know any situation like this in high dimension, except Laughlin quasi-particle for the fractional quantum Hall effect, which can carry charge 1/3, for example. But this is a very specific case. In 1D, it's practically the rule rather than the exception. So these excitations, they have a name. They are called spin-ons. And these are very weird objects. As I said, it's a non-local excitation. So what is a spin-on? It's taking the system and turning all the spins from this position to infinity. So again, it's an excitation you cannot create by a local effect on a system. The only thing you can do is create them by pairs, but then the system can split and separate this spin-on excitation at will. This excitation have a hidden topological order parameter. We'll discuss this tomorrow now, not tomorrow, Thursday. And again, topology is the rule in 1D rather than the exception. And because now you see that my magnon is splitting into two excitations, it means that instead of having a very nice dispersion relation, actually I will get a continuum of excitation, because I can split the momentum between my two spin-ons at will, as long as the sum of the two momenta are reproducing the initial momentum. And each one of these excitation has an energy as a function of its own momentum. So the energy of the particle is the sum of these two energy, and I can spread the energy in many, many different ways. So instead of having one very well-defined energy dispersion, I have now a continuum of excitation. So here is this continuum of excitation as a function of the momentum. I let you play with a constraint to check that this form is indeed the right form. That's the only place where I can find non-zero excitation. But nevertheless, instead of having a kind of single curve here, I get this continuum. It has a name. It's called the de Cloizeau-Pearson continuum because it was identified in Bethe-Ansatz solution. But this is a very generic property, which is not resting at all on the fact that models are exactly solvable. You can do even worse. Let me do it for a fermion, a real fermion with a charge and a spin, and see what would happen. So it's a cartoon, but using the bosonization technique that I explained, trust me, one can really get the calculations that will confirm what I'm presenting to you as a cartoon. So let me remove one particle, which means I remove a charge and I remove a spin 1/2 here. Now I do the same thing. I apply the, let's say, spin exchange. So I flip the spins. And you see what happens. Charge is not moving, but my spin excitation is now somewhere there. So I have a region in my system where I get two spin down and spins have turned compared to their initial position. So that's exactly my spin on. So my electron that has been removed has split into an excitation which carry a spin but no charge. On the other hand, I can let the charge move, jump, and essentially you see what happens now. Okay, let's accelerate. I have my missing particle, which is surrounded by a perfect antiferromagnetic order, but which has been shifted by one lattice spacing. And this is an excitation which doesn't entail any modification of the spin order. It's up, down, up, down, up, down, up, down, up, down, but in which one charge is missing. And this excitation has been called a holon because it carries a charge, but no spin. This is a phenomenon which goes by the name of spin charge separation, and which is one particular case for a particle with charge and spin of the fractionalization that I was mentioning before. So it's very common in 1D to get this possibility for excitations to fractionalize and decompose into sub-excitations. Now, cold atoms are particularly good to test for this. I think Emmanuel might talk about this, but let me flash you a preview since the experiments were done in his group, which is using microscopes similar to what you saw in the talk of Vassem back. Then you can analyze what happens if you have 1D Hubbard chains, and then you can use the microscope to check explicitly where are the spin down, where are the spin up, and then you can measure the type of order that exists in this system. So maybe I'll go directly to the result. You see these very nice antiferromagnetic correlations that exist in the system. And you can even do better. You can check that indeed you have regions where there is a hole, but that this hole is surrounded by the type of stretch antiferromagnetic surrounding that I was discussing. So this is my holon here, which is surrounded by down, up, down, up, down, up, down, up, down again, and there you get again a hole. So the top line is measuring the spin up, the bottom line is measuring the spin down, and because you have local access to every position and every site in the problem, you can really test locally this type of order parameter, and you can literally test that there is indeed spin charge separation that is happening. So this is one other aspect of the weird 1D physics which is happening. Now, just to finish, you could say, why don't I have the same thing in higher dimension? Well, let's try it. Now I don't have a 1D chain, but I have many 1D chains. And I will just remove one particle in the center chain. And let's see if I can get exactly the same thing than before, namely the splitting of this excitation in terms of spin on and hole on. Well, we get the spin flip, but look at what happened. All these regions here, I get 3 spin up which are close to each other. So if I have antiferromagnetic correlations here, the system will be extremely frustrated by having these very badly turned neighbors here. So actually, if I try to flip on the central chain only, I'm creating a string of very high energy as the spin on is moving away. And same thing if I make it move on the other side. I'll create again a frustrated string of high energy. So if I have other chains, what happens is that, yes, I could do the same thing, except that now my spin on and my hole on are like quarks. They are bound together by a string whose energy is growing as the lengths between the spin on and the hole on. So this forms a bound state, and this bound state is my quasi-particle, which carries the charge and the spin. So at least the naive spin charge separation is not possible when I am surrounded by other chain. And it's only the possibility in 1D to turn completely half of the system without consequences, except the local contact at the point where I've done the transformation, that allows for this spin charge separation. Voila, I think it's a good point to stop here. You get here the quasi-particle. I don't want to show this today. So let me stop here. Tomorrow we'll continue our tour by trying to see how we can go beyond the Tomonaga-Luttinger liquid, because again, for the moment, everything works. It's not fun, even if it's beautiful to test all this with cold atoms. So we'll see how we can perturb a little bit this very nice system by A, putting a lattice and going to Mott insulators, and B, by putting disorder, and see whether we can have Anderson localization and a little bit weirder effects as you already started to hear in many courses before. Let's see what happens when we try to do this in interacting one system. Okay, on that I stop, and if you have questions, I'm of course ready to take them.
Thank you very much, Thierry. And indeed, the floor is open for questions.
I guess maybe this may be jumping a little bit forward, but like in these questions of like charge spin delocalization or separation, we have to include the spin degree of freedom, which is something we didn't start at with our literature. Is that, should I, maybe can you give us a picture of like, how should I get, do I basically get two coupled Luttinger liquids and fractionalization kind of emerge from that, or how?
Exactly. So the bosonization formula that I showed you, if you have two spins, degree of freedom, you bosonize the spin up. So you introduce a field phi up and theta up, and you bosonize the spin down and you introduce a field phi down and theta down. So you can bosonize species by species. Same thing if you have two chains or three chains or four chains. And then it's just a question of having to deal with this a larger number of fields. And the fact that new terms can appear in the Hamiltonian, which are not simply quadratic. So actually tomorrow we'll see, not tomorrow, Thursday, sorry, I keep insisting. Thursday we'll see that actually if you put a lattice, one such term that will appear is a cosine of the field phi. And it's the same thing if you have two spin species, there will be cosine of the difference of the field phi up minus phi down that will appear. How you deal with this more complicated Hamiltonians, of course, that's the reason why not all problems are solved in 1D and there is still work to do. I just want to point out that technically there is nothing that prevents you from bosonizing an infinite number of chains. So dealing with a 3D system as writing bosonized coordinates for each one of the tube and then putting the coupling between the tubes, that's perfectly possible. The problem is that now the change of variable is not as efficient as if you had a single chain. So you're perfectly correct. We can perfectly bosonize spin species by spin species, and that's actually the way it's done for the fermionic Hubbard model. Except then it's convenient to introduce the sum and the difference. Phi up plus phi down, you call phi rho, this is the charge sector, and phi up minus phi down, you call it phi sigma, and that's the spin sector. And you will find that these two sectors miraculously decouple completely, which is the mathematical way of seeing the spin charge separation. So the spin charge separation, I let you do it as an exercise if you want to do it. The spin charge separation comes very beautifully out of the bosonization as the fact that the Hamiltonian become the sum of two uncoupled sectors.
Awesome, thank you.
You're welcome.
Sorry, I have a question regarding the program that you were describing earlier, the, doing numerics on one part of the phase diagram and then doing the field theory. So for spins and fermions, you have a great numerical approach that is DMRG and NPS calculations. Yep. Do you have something similar for bosons, or what's this numerical approach?
Yes, so there are several numerical approaches which are possible. So first, if you're on a lattice, you can perfectly use the MRG MPS. You just need to limit the Hilbert space. So people say, oh, I don't want to have more than 8 bosons on a single site, which means you have difficulties to address the very weakly interacting bosons, for example. But usually their perturbation methods are not too bad. So you can perfectly use the MRG for bosons as long as they are on the lattice. If you are in the continuum, quantum Monte Carlo is a great method. It works very well. And then the question is to find the proper nice quantity that you will compute with your method in order to extract these Luttinger liquid parameters. So for example, you can extract the superfluid fraction, actually the superfluid fraction in quantum Monte Carlo, which is measured by computing the winding number, is a great way to extract the product U times K. and the compressibility can be computed by the same usual trick of adding particle, removing one particle, and computing the difference of energy of the system. You can also use for bosonic systems Bethe-Ansatz models if they are available. But I would say from the numerics, quantum Monte Carlo and Giamarchi are probably the two most used techniques for bosons.
When you say,
yeah,
you can go ahead.
Okay, go ahead. Oh, thank you. Can I ask about so when you're showing the spectrum of just the green function, like it seems like there is a kink, and
yeah,
I just wonder
that's a very good question. I was looking at the picture and thinking the same. That's a good question. I think it's a blurb of the way the image was produced or copied or whatever. I'll check. I don't see any reason why there should be a kink here, but I agree with you. There is a very distinct impression that there is a kink here, here, and here. So, okay.
All around the same, yeah.
I think it might be because actually getting this solution, it's coming from the Bethe-Ansatz, but unfortunately it's not a nice sort of single analytic formula that is plotted. Actually, the way it's obtained is by summing many terms and making sure you get most of the spectral weight. So it's also possible that in the program which did that, there was a little blurb connecting to half of the calculations or whatever. But I'll recheck. That's a very good question, and I don't have the answer. My impression is that sort of this kink is not there. It's an artifact, but before swearing it and selling my soul to this answer, I'll recheck. So.
Okay, thank you.
I guess in the case of fermions, isn't there an instability of the Fermi surface that occurs exactly at 2kF? Wouldn't it be?
So for fermions, if you have free fermions, then you get essentially this curve. Because that's the 2kF scattering. Let me show you with the iPad. If I have free fermions, what happens? You get excitations like this. And now you can take low energy excitations can do this. So this is what will produce this curve, this part of the curve. Or you can take something, but then you have to bring it on the other side of the Fermi surface. And that's what will produce the excitations around 2kF. So you get a curve which is sort of like doing like this. And for free fermions, there is no other by the way, 4kF or 6kF or 8kF, which means for free fermions, all the other amplitudes in my expansion would go to 0. Okay, but if I start to put interactions, I will get a component at 4kF as well, and so on and so forth. It's actually a fun exercise to try to see on the band how I could produce terms which exist at 4kF by playing with the periodicity of the Brillouin zone and the fact that I can squeeze interaction process in the scattering. But for free fermions, that's it. You can get it's called the Lindart function. You can get exactly the curve which corresponds to actually the Tonks limit for the bosons, for the density spectrum.
I was thinking when you said in 2D in the spin charge separation, there's a problem of there's a lot of energy consumption, right? I guess in the case where the hopping helps you, like you have a negative J hopping, then they can compete and you can have spin charge separation, right?
So don't get me wrong. I'm not saying that spin charge separation is impossible in 2D. I'm just saying the naive mechanism doesn't work. So you have to imagine smarter way to get this kind of deconfinement, and people are trying to find it in frustrated systems and so on and so forth. Just to show you that this mechanism works, if I take localized spin, the same mechanism will apply for the confinement of two spin-ons. You have this string, which is binding the two things. So you can solve it. It's a two-body problem with a linear potential. This is airy function. This is a nice exercise in quantum mechanics. Sorry, let me just show you this. Here is what you would predict for the spectral function with a lot of resonance here, which corresponds to the bound states of these two. It's like hydrogen atom, if you want. You do bound state of two spin-ons linked to the presence of the other chain. And what you see below here is the theoretical calculation of these bound states. And the dots here are an experiment which is done with quantum spin chains by the Béatrice Grenier and Virginie Simonet in Grenoble. And you see that this matches very beautifully the theoretical prediction. So this confinement of spin-ons, it can even be seen, not just say they stay together, but you can even analyze the spectrum that would be produced by this confinement of spin-ons. I would love to see a similar experiment done in a cold atomic system, for example. But this can be done using quantum magnets in condensed matter, and it works pretty well.
Thank you.
So Thierry, I'm going to take my initiative as one of the organizers to ask a question as well. So in talking about fractionalization, you brought up the Laughlin state.
Yes.
In your opinion, either personal or analytically, would you say that that connection is actually really related to the fact that quantum Hall systems are almost 1D systems anyways?
That's a very good question. Whether it's very tempting to say that when you have Landau levels, in a way, dimension is not playing any more role, and that's why you get potentially this kind of fractionalization, which is possible. On the other end, the mechanism which is coming from the Laughlin wave function seems to be so specific, although people have tried Laughlin wave function in 1D and they work pretty well, I would say. So that's a good question, and I don't know the answer to this question, whether there is a deep reason why these two phenomena are related.
Right, because the sort of extension of that I remember from, so I got my PhD in condensed matter physics students. There's this thin torus limit where Laughlin collective excitations turn into spin domain walls or domain walls of some kind. And that's the sort of thing that makes you think that somehow hidden in the bulk, the 1D physics is still driving the fractionalization phenomena.
You know, there is a very nice paper by Charlie Kane where he reproduced the Hall effect by doing this with coupled 1D chains, but gapping the modes in the bulk. So it's very tempting to say, yes, there is a deep connection, except again, I will not sort of say that without, you know, having something to put seriously on the table. But yes, it's very tempting to imagine that we can connect the two situations. And again, in some cases, there was connection that was established between Hall effect and, of course, 1D physics, if any, the edge states, which are chiral Luttinger liquid, which is very, very clear. But even in terms of bulk excitations, you can recreate the fractional Hall effect with coupled 1D chain. But you know, there are other situations like spin ice and things like this where people have fractional charges. So again, finding mechanisms with gauge fields where you can produce these fractional charges, it exists. Whether it's linked to this particular mechanism, that's a more complicated in a way question.
All right. Well, thanks very much. And given that we're sort of eating into the lunch break right now.
Yeah, I'm sorry. I'm eating into your lunch break. So
and maybe you're eating into your dinner break.
That's okay. Okay, so have a good lunch and see you very soon.